Welcome to my presentation. My name is Menna Hammam, a Master's of Science in Construction Management graduate from Arizona State University. I would like to start by thanking the co-authors of this research project and acknowledge Mortensen Construction and Corbin Electric's help in accessing data center job sites and providing valuable input in this research. My presentation discusses a new look at designing electrical construction processes, and it's a case study of the cable pulling and termination process on data center construction sites. The outline of this presentation is giving some background about the research project and data center construction. The current cable pulling and termination process will then be presented. An overview of a proposed future state of practice will also be discussed. The motivation of conducting this research is the growth in data center construction market over the past decade, while the construction industry is suffering from labor shortage and lack of needed digitization. Although mechanical, electrical, and plumbing scopes make up a large portion of any construction project's value, especially in data centers where electrical and network cabling are crucial elements, specialized subcontractors such as electrical subcontractors are lagging behind in productivity. This is why there is a need to start reconsidering existing processes, practices, and utilizing technology, a tool that is already available to us in order to improve productivity. The authors are focusing on cable pulling and termination in this study because it constitutes a large scope of any data center project. It is labor-intensive and poses various safety risks to our craftspeople. Several approaches have been taken by researchers to introduce automation in construction, but none of them looked closely enough at the existing processes before attempting to introduce automation. This research will look at how the existing cable pulling and termination process could be optimized for automation. There are two ways to run cable in a data center, either overhead, which is basically over the equipment, or underneath the data center raised floor. Cables are housed by ladder trays, basket trays, or cable trays. The design of the data center cabling network usually dictates which method to be used. This research adopted a three-step methodology. In the first step, the authors visited data center construction sites, interviewed crew members, including electricians, project engineers, and superintendents, to create a process map of how cable is currently being pulled on job sites. This process map was then validated by industry experts who have at least 10 years of experience in construction and have worked on 3 to 4 data center projects. The experts provided feedback about the fundamental activities required to accomplish the process and how some construction sites might do things differently. The authors then used the validated process map to analyze and categorize activities in the current process and look for areas of improvement. After determining which activities need to be automated, the authors investigated how other industries have successfully automated similar activities. Let's move now to the current process. The detailed process is provided in the paper, but for the sake of time, a summary of how activities were categorized will be provided in this presentation. There were 4 major types of activities that needed to be improved. First, unwinding cables from reels and cutting the required length of cable, which falls under activities that cause safety injuries. This activity is a source of back sprains and hand crushing. Moving cable is also associated with back sprains since power cables can be very heavy in instances. Material handlers were observed carrying cable over their shoulders to move it from staging area to pull area. This makes this activity also labor intensive, since long runs usually require more than one person to carry. The activity of pulling cable through trays is labor intensive, time consuming, and associated with safety injuries. The current practice is pulling string through run path, tying a string to cable at one end, and then using the string to pull cable. This involves double work because pulling occurs twice, and this is why it is time-consuming. This activity is also labor-intensive because it needs at least 2 electricians to pull a single cable run, and usually one person who can move in between through the equipment in case the cable is run overhead in order to get cable through obstacles. Terminating cable, labeling, grouping, and testing are repetitive and time-consuming tasks that don't require any skill to complete. According to interviews with electricians, it takes an electrician an average of 24 to 48 hours to terminate a single uninterruptible power supply or server. Labeling cable to ease future maintenance is also a task that is very basic and repetitive. After analyzing the activities in the current process, the first step was selecting activities that could potentially be moved off-site by utilizing prefabrication in order to minimize the amount of labor and time required on-site. The second step was eliminating any activities associated with the activities that have already moved off-site since they no longer add value to the process. The activities remaining from step 1 and step 2 were then investigated for automation potential by looking at similar activities that have been automated in other industries. The following slides will present a summary of the proposed improvements to the current process. The authors propose replacing the current practice with creating a holistic 4-dimensional building information model where cable runs would be modeled. The model would potentially contain information such as cable run identification number, length of cable, termination type, and would be tied to a pulling schedule. With access to the 4-dimensional model, the manufacturer would be able to manufacture pre-terminated cable runs that would be delivered to the job site as per the pulling schedule. As you can see in the current process, there are 4 steps required to get the cable to the pull area upon arrival of the cable reels on site. Whilst in the proposed process, the pre-terminated cable runs would directly be moved to the pull area, saving some work done on site. The pre-terminated cable would also save a step in the termination process. In addition, the 4-dimensional model will aid in the use of autonomous equipment and mobile robots in receipt acknowledgement and inspection. Agile mobile robots currently used on construction sites are equipped with 360-degree cameras that would be linked to virtual design and construction software. These robots have the ability to perform inspections and avoid obstacles and people when moving around, so they would potentially help with transporting cable runs around the job site. For cable pulling, the authors suggest using snake robots that are currently used in accessing unknown and challenging environments. Also equipped with cameras, they are able to capture high-quality images of tubes and vessels. Pre-programming snake robots to run paths and potentially pull cable along would be an ideal scenario. In more complicated runs, they would possibly be run by an operator similar to how drones are currently operated. So far, snake robots have been developed for inspection and maintenance application in the field of construction. As for connecting pre-terminated cable to equipment, labeling, and grouping cable for organization, surgical assistants would be of great help. Surgical assistants are currently being used by surgeons to perform teleoperated surgical procedures inside the human body. The surgical assistant acts as the surgeon's eyes and hands, which are designed to work in tight space inside the human body. During a surgery, one hand holds a lighted high-definition camera that acts as the surgeon's hands, when the other hands hold the rest of the surgical tools. By changing the tools used in surgery to tools used in labeling, grouping, and connecting cable, the authors suggest that surgical assistants would be able to accomplish these tasks, especially that they are repetitive as mentioned previously. One of the most important advantages of adopting the proposed process is leveraging the skills of craftspeople in operating the robots by patiently re-educating them. This will also encourage younger generations to join the construction industry and help with labor shortage. Robots can work 24/7 under human supervision. They need no breaks, no vacation, and with the current COVID-19 pandemic, they provide an opportunity of decreasing contact between workers by touching equipment and materials. Safety concerns previously mentioned will also be reduced. Some limitations have to be taken into consideration when considering the process improvements. Extra cable length in pre-terminated cable can be problematic to handle. If cable is damaged, the replacement time will be longer because pre-terminated cable will not readily be available on-site. In order for the process to be accomplished efficiently, accurate and timely schedule updates must be performed. Areas future research would explore are implementing and validating the proposed process on active projects. A cost-benefit analysis will be beneficial in determining if the benefits brought by the process outweighed the costs and investments to adopt it. A very important area of future research is investigating the development of customized robots for the previously mentioned tasks by learning from other industries. Thank you so much.